In this lecture, I'll be citing very heavily the first chapter of Cooper, Heron, and Heward's Applied Behavior Analysis, 3rd edition, the White Book, 2020. Please forgive me for citing them a lot. In this lecture, I'll be committing a sin. I'll be doing many naughty things in this lecture series. Just kidding, not actually. But I do feel conflicted. I'll be doing something. I'll be inflicting upon you guys what I myself know what it's like to be inflicted. If that makes sense. I'm an undergraduate. I'm a senior, but I'm still an undergraduate, so it's still fresh for me. I know what it's like for you to take an introductory to whatever class. Instead of the professor getting right into it, they have to give all these foundations and talk around the subject and talk about the history, and they can't get into it because they have to give some foundation for you to build your knowledge upon or something. That always annoyed me. Always frustrated me. They couldn't talk about the subject at hand. They had to talk around it. And yet, that's what I'm going to be doing here. I'm going to be doing the very same thing. In this lecture, I'm not even going to talk about behaviorism. I'm just going to talk about science. Because I really do think it's important for you to understand science as a foundation before we understand how radical and unique behaviorism was as a take on science, as psychology. And so I hope you can forgive me as I'm going through my own personal transformation in gaining some forgiveness for my own professors. So this lecture is on science as a whole, and let's get right into it. When Bertrand Russell was asked about the difference between philosophy and science, he said that science looks at the questions that we can answer, while philosophy looks at the questions that we can't. It's a very eloquent answer. I quite liked it. Never forgot it after he said that. And it appeals to something in us. We like to think about it. We like to think about science and philosophy as different things. That there's a difference between assumption and fact, between a perspective and the truth. We like to think about science as what we know, while philosophy has to do with what we speculate about. This feels good, but this understanding of science falls apart when we investigate what science really is. The question, how do scientists know what they know, is not at its core a scientific question. We cannot use empiricism to empirically define what empiricism is. We can't use science to define science. We can't collect enough data to try and come to an adequate conclusion about what data is. The question of how should science be conducted is not a question of science itself, because it is not a question we can answer. Instead, it's philosophy. It's one of those damn questions that we can't. Now, for a very brief definition of what science is, this particular definition, or philosophical argument, is from Applied Behavior Analysis, the White Book, by Cooper, Heron, and Heward, 3rd edition, 2020, in the first chapter. Science, this is as a quote, science is a systematic approach for seeking and organizing knowledge about the natural world. The overall goal of a scientific field is to achieve a thorough understanding of a phenomena of study, end quote. For example, the scientific field of biology aims to achieve a thorough understanding of the phenomena of life, and chemistry to molecules, astronomy to the universe, physics to forces, and so on. All sciences rely on philosophy, because to be able to ask questions that we can answer, we first have to get past the wall of questions that we can't. So let's give an example, a real personal one for you, right? So you're trying to understand what behaviorism is. And that's a question that you can't answer. We can understand what behaviorism is. But to be able to do this, to be able to even watch this lecture series and take it seriously, you have to get past a number of questions that you personally can't answer. For example, how do you know this is not the Truman Show? How do you know that every single person you've ever watched, ever known, every family member, every friend, how do you know that they're conscious like you are? What if I'm a robot? And everyone else is a robot. Your mother, your father, your sisters? What if this is the Truman Show? A bunch of aliens tune in from 5 to 9, or 2 to 3, whatever the time they watch, and they just laugh. Look at this little critter, trying to understand behaviorism. Ho, ho, ho. How do you know that this isn't all a simulation, that this isn't a chair or a table, but data? You don't know. And yet you're here, learning about behaviorism. How did you get past this unanswerable question? Well, you probably did what a good scientist would do, which is simply that you made an assumption. And that's what scientists do. They make assumptions about how the world works, about what the world is, how it operates, and about what attitudes we should have when observing that world, and also about the analytic goals our observations can be used for. We can back these assumptions, though, so this isn't just meaningless conjecture. We can back these assumptions with good philosophical argument. And if we can understand those assumptions and their arguments, we can understand the philosophical foundation from which science is conducted. So here I will describe science as a philosophical argument with its assumptions, attitudes, goals, and basic processes. And again, this philosophical argument is based on the explanation from Cooper, Harden, and Heward, 2020, The White Book, Applied Behavior Analysis. So let's get right into it. One of the most core, wide-spanning, dramatic assumptions of science is the assumption that science is possible. The scientist assumes that science is not pointless, not purposeless, that it can be done. The scientist assumes that trying to look for systematic explanations through the study of the natural world is not a pointless and impossible endeavor. While this sounds simple and obvious, this is actually one of the hardest assumptions for people to swallow, one of the hardest pills to swallow when thinking from a scientific perspective. This is because of what it means. Scientists have to assume that in every effect there is a cause, and that the rules of the universe do not change, and that nothing happens by accident, but by laws of the universe out there to be studied. It is to say, and this means that if we are to wear the scientist hat, we must also put on another piece of attire, and that means we must put on the attire of the determinist. We must wear determinist clothes. This is one of the most foundational assumptions of science, determinism, that in every effect there is a cause. And the reason this is so controversial is that some people want certain phenomenon to have no cause, to have no explanation, no law to be studied. Why are you thirsty? Just because I was, and that's it. Not to the scientist. To the scientist, there are reasons, causes that determine everything, and such causes can be studied, such as science. Another assumption of science is that science can be built on and should be built on empiricism. Now, what is empiricism? Empiricism is the practice of relying on objective observation. Now, what is objective observation? Objective observation is observations independent of the tastes, beliefs, or opinions of the observer. This is critically important, what I'm about to say now. If you're dazing out and you're not paying attention, snap back into it right now. This is critically important, this next point I'm going to bring up. And it's going to be important for the next lecture too. All right, you ready? You ready? If someone makes me an omelet for breakfast, I can empirically observe if there are mushrooms in my eggs or not. I can observe it. You can observe it. The cook can observe it. My grandma's sister's daughter can observe it, independent of their culture, their upbringing, their past, their personal ties. They can observe it, as so can I, if empirically there are mushrooms in my eggs or not. Yes? In this way, we may say that the question of the presence of mushrooms in eggs is an empirical matter. Now, my disgust for mushrooms is not an objective observation of the food itself, but it is a subjective one with personal ties to me and my palate. It is limited to me based on my opinion, but empiricism has no personal ties. It is used for those empirical matters, and that is what science has been made for. So we have talked about two assumptions. One, that the world is deterministic, and two, that we can and should make objective observations for science to be conducted. Now, let's talk about the goals of science. This is one of my favorite parts of this lecture. The scientist does not merely ask questions because they have nothing better to do. The science is not conducted on the weekends, but during the week. They do not ask questions merely because they are curious, but because they hold a more structured, a more cultured, a more dignified, thorough kind of curiosity. This is because the scientist is aware that what motivates curiosity is not whim, but an aim. The scientist has precision to their curiosity and therefore their questions because they know what their questions aim at. What is known in science as an analytic goal. There are three analytic goals you can aim at, and depending on the analytic goal that you have, it shapes the questions and therefore the methods that you can use to answer it. And so, for this next section of the lecture, let's go over the three analytic goals of science. The first analytic goal of science is called description. It is the systematic observation of a specific phenomenon to understand what the hell that phenomena is. It is the collection of facts, the sharpening of details, the measurement of data for the sake of having data itself. When as a child in school, you first learned about the planets and the moon and whatever Pluto is now, of the solar system, you were early scientists of the descriptive variety. The components of a molecular compound, the ethnic composition of a culture, the age of the earth, the species of an animal, or of its number of legs, this is what fills the dreams of the descriptive scientist. Now, the second analytic aim of science is called prediction, and usually follows after description. When we observe enough things, we tend to notice that things tend to happen in clumps. Things tend to happen together, or one after another. They tend to, the things we observe, they tend to relate in some way, but we don't know how. So we say that they tend to co-relate. The scientists came up with a very clever term for this co-relation. They called it a correlation. They notice that people with cuts tend to heal. If you plant a seed, they tend to grow. The people's brains tend to light up in this specific area when you throw them into an fMRI and when they laugh. These are predictions. Some predictions seem to be lawful. All people seem to die. Other predictions seem to be probabilistic. Those people over there who smoke cigarettes and don't exercise, they don't seem to last as long. Predictions can tell us a lot, but they don't tell us why. You can predict that a cut will heal or that a planted seed will grow, but it doesn't mean that you know what causes it. Why do those who seem to meditate seem to be happier? Or how does a blip in the brain lead to laughter? We can never know without reaching for the third analytic aim of science: control or influence. Easily regarded by many as the highest analytic aim of science, the tip at the top of the pyramid. To understand control is to understand the very famous, almost celebrity status in science, the dynamic duo of the independent and the dependent variable. Hand gestures, wow. To understand cause is to know what controls a given system or a subject's behavior. And it was control that changed humans from monkeys into evolutionary gods, with refrigerators that keep things cold, and pills that kill diseases, lights that illuminate our buildings, and have water fountains at every floor. If knowledge was the apple in the Garden of Eden, one of its seeds was the science of control. Now, for description, the challenge of science is in the collection of data itself. For prediction, it is the collection of data in ways that show correlations or patterns. For control, we must be even tighter with our methods. We must not only collect data on variables that relate to one another, but we must also manipulate conditions so we can show exactly what that relation is. To snuff out the relationship between two variables, we must rely on very specific processes. These two processes that we'll talk about here are called experimentation and replication. And because scientists aim for control, these are two keystones of their practices. So let's talk about experimentation and replication. Let's say you go on a date. A date with a guy named Steve. Steve's a nice guy. He has a nice fit, a sharp jawline. You guys hit it off, have a lot of fun at night, and it's the next morning you realize you wake up in his bed. But you wake up and Steve's not there. And you look around and all of a sudden you smell smoke. You are jarred. You're a little bit awake. You're afraid. What's going on? So you get up and you hurry downstairs. And then you find Steve burning a whole smoke of incense. Enough incense that it looks like a bomb went off. And there's Steve, still in his underwear, hopping around, shaking a tambourine that he got from the dollar store, and beating on a drum that's an upside-down paint bucket from Home Depot. And he's dancing around. Still in the stairs, you look down at Steve and you say, "Steve, what are you doing?" Steve turns around and looks at you and then smiles and says, "Oh, good morning. I'm doing a dance to keep the rats away." You say, "Steve, you have rats here?" And he says, "No, I've never had a rat here, and I've lived here for many years." Confused, you look at Steve and you say, "Steve, if you've never had any rats here, why are you doing this dance? How do you know that your dance has anything to do with the rats?" And Steve looks at you and he has this weird, almost pretentious look, and he smiles at you and says, "Well, isn't it obvious why I do the dance? Can't you see how well it is working?" Any rational person, including a scientist but not limited to, would walk straight away from a scene like that. It is only the belligerent and untactical scientist who maybe doesn't have a gut or an amygdala or a personal sense of safety that would stay in that situation and try and pick that battle. Because obviously, the absence of rats does not prove that your dance was the cause of it. To understand causal relations, one must be able to identify and manipulate the factors that influence a certain phenomenon. So, if you were, I know you are not, but if you were a misguided scientist who does not value their time, You might try and show Steve the rats in your own lab. And you might have them do his little dance to see if it does anything. If given a wide space where there is both food for the rats and Steve doing his little routine, do they evacuate it and never return, or do they simply hide, waiting for the dance to stop, maybe light a cigarette, play some music, waiting for Steve to do his thing and then the night to fall so they can ravage the place? Not literally, but you get the idea. This process of measuring variables of interest, number of rats occupying a space with food, under different conditions, morning dance or no dance, to see the relationship is called experimentation. And it is the one arrow humankind has in its quiver to aim at the analytic goal of control. Through experimentation, we understand influence and control. But let's say Steve says to the scientist that the experiment has already been done before. It's already been done once. They did the study. It was a very great study, yes? They did this tambourine dance. They covered themselves in cooking flour, and they hopped around and made a mess. And the rats were away. Great, the scientist would say. If, as you say, it's only been done once before, then it has not been replicated, and thus must be done again to see if it can be more fully believed as true. This introduces the idea of replication, which is simply having experiments done multiple times to see if we can find the results repeatedly. So when researchers first looked at the relationship between the MMR vaccine and autism spectrum disorder, they originally believed that there was a link. Dun, 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 dun. The MMR vaccine was causing autism, they said, and then they bulleted it out on newspapers and shot it out across America. But this initial study was done on 12 children with numerous methodological flaws. When this research was replicated in a rigorous study with 500,000 people in it, they found zip. Nada. Zero link between autism and the MMR vaccine. Replication is the scientist's way of saying, no shot. Wait, let me see. And then either being proven right or wrong. On top of assumptions and methods, there are also a number of attitudes that are held dearly in the scientist's heart. There are two in particular that are especially important. One is known as parsimony, and the other is philosophic doubt. Parsimony is the bias towards the shorter of two explanations when both of them are equally true. Basically, it is the scientist's way of saying, what's the TLDR? And keeping it relying on the TLDR as long as it keeps the conversation going. In science, explaining stuff is complicated enough. You do not need to add extra variables, rely on unnecessarily difficult explanations, or fall to extremely complex theories when a simple one already exists and works equally well. Scientists don't have no patience. They've used all their patience enough already on data collection when they had to translate 4,000 data variables from handwritten chicken scratch to some Excel sheet. And so, don't rely on a longer explanation if the simple one works equally well, especially if the longer explanations don't allow for better results. That's parsimony. Secondly, the second attitude is called philosophic doubt, and it's what I like to call the analytic squint. I remember the first time I saw the analytic squint with my own eyes. I was in first grade, and I had just come home from school, and my mom asked me, how was my day? And I went off, and I unraveled all the events of my day, and then I told her about gym class, where we played tag, and the teacher played along. And there was a moment when the teacher was going to tag me, and he was it, and I was cornered, and I had nowhere else to go. And so you know what I told my mom? I told my mom I jumped over the gym teacher. The good scientist, and in this case, the good parent, is a skeptical one. That means that no fact, no feature is held sacred, holy, or divine. We take no truth for granted. There are no commandments chiseled in stone. What stands is only what can survive that piercing stare. No fact or feature is given immunity to the analytic squint. There is only tentative positions. And so this leaves us with our final argument as to what science is, as quoted again from Cooper, Howard, and Heward, 2020, The White Book, Applied Behavior Analysis, 3rd edition. Quote, "Science is a systematic approach to understanding natural phenomena, as evidenced by description, prediction, and control, that relies on determinism as its fundamental assumption, empiricism as its prime directive, experimentation as its basic strategy, replication as a necessary requirement for believability, parsimony as its conservative value, and philosophic doubt as its guiding conscience." If this makes all sense, great. It'll get a lot more hairy as William James walks into the room, beckoning, calling for psychology to be a science too. So I look forward to seeing you in the next lecture. Becking. Okay. That was not bad. I had to look at the script a lot, but you know what? I haven't had enough time to practice it. It's not terrible. Oof. But I'm exhausted. My gosh. I hope that worked. Okie dokie. 26 minutes, Jesus.